All right, guys. So we're having our test on Monday. It'll be in the auditorium. We're gonna have a help session on Thursday. I'm sorry I can't do it on Friday. I'm not available on Friday. I have other business going on. But we'll have a help session on Thursday at 2 p.m. I'll send a message out telling you where. It'll probably be over in Beauregard somewhere. Thursday at 2 p.m. we'll do a help session. I'm sorry if you can't make it. I'll record it. I'll do my best to record it. Sometimes it doesn't always work out, but I'll record it if at all possible and post it to the help session website on the link on the website. Also, notice that you have a couple of assignments due. You had a reading assignment due last night, but you have two big ones due. Hopefully many of you have already done this one. That's due on Thursday, because remember it was supposed to be due the previous week. But then you have one that's due on Friday as well. There is a mistake on one of those questions. I think it was number 5. A student and I found it earlier today. And I'll send a message out to you with the answer for that one and a description of how you're supposed to work it. All right, I think it was number 5. Is that the one with the 4 charges and you move the charge to the center? Did you get it right? No. But I'll send it to you and the solution, the answer that you should put, and then the act question. Okay? What else? Test on Monday. I think everybody here has had my test. Have one transfer, but the test, is normally 26, 27 multiple choice questions. In the auditorium, you get an hour, come at 10:45, you get until 11:45. That's it. Any questions about that? Oh, what's on the test? Chapter? What?
Chapter 1 and like part of chapter 2.
All of chapter 2? Part of chapter 2. Right. We're not going to see capacitors at all. We might get to capacitors a little bit today, but I decided we're just not going to have any capacitors at all. That's sort of the second half of chapter 2. So as you're going through the old exams, if you see anything with a capacitor, you say, if it says capacitor in the problem, don't even look at it, okay? We'll get to that. So we might get to it today, but it's not going to be on the exam. On Friday, in class, we'll also have a review. So Thursday we'll have a help session, and then on Friday we'll have a review as well. I might do a little bit of time with capacitors, but we'll allow at least half the time for review questions. Do y'all have any questions about anything coming up? No? You know why? Because you're awesome, that's why. Now, if you had questions, you wouldn't be any less awesome. But, let's see. I told my wife I've been trying to be more affirming in my class. Do y'all feel affirmed? You're awesome. You're awesome. We're being affirming of one another. Okay, y'all ready? We're going to do equipotential lines. We're almost done with this chapter, and then we'll do the clicker questions for this. Actually, let's go ahead. We'll do equipotential lines first. So, an equipotential line, if you're in the lab, you've seen this already. Y'all did equipotential lines, but it's a line, or if you're looking in 3 dimensions, a surface, but we're just through 2 dimensions, so it's a line where the potential is equal, right? It's equal or the same. Along these lines, the change in potential is 0. The change in potential there's no change in potential. Also, the work required to move a charge along those lines, well, what is it? Is it positive? Is it negative? Or 0? If we move a charge along an equal potential line, how much work is required to do so? It's 0. Remember, because work is equal to Q times delta V. And so if I have a change in potential of 0, then the work required to move an object along that equal potential line will be equal to 0. So the work required to move a charge along an equal potential line, I'm going to call an EP line for equal potential, is also 0. it would be sort of like if you have a mountain. There's your mountain, and you go around the mountain, but you never change height. That you just go around the mountain at the same height. You're not actually changing your energy, so it requires no work to move around a mountain at that same height or at that same potential. It's sort of the same idea. Moving around an equipotential line. In fact, you know, if you like looking at maps, y'all like looking at maps? Like topographical maps? The little lines on the topographical maps, you can think of those as equipotential lines because they're all at the same altitude. So the amount of work required to go around those topographical lines are equal to zero. And remember, this sort of comes about from our definition of potential energy, which is our potential difference, which is delta PE over Q. So if I have a change in potential of zero, then my change in my potential energy is also to zero. Like with the mountain, my change in potential energy is zero, so no work is required to move along that equipotential line. The electric field is always perpendicular to the equipotential line. It sort of has to do with calculus and how that all works out, but the electric field is always perpendicular. So if I were to draw my equipotential lines, they'd look like this. There would be lines that would always be perpendicular to the field lines. Notice that they're always perpendicular when they intersect with a field line. And similarly over here, always perpendicular. Now I can draw equipotential lines at different positions, so I could also draw an equipotential line out here. And just like on a topographical map, when you have different lines denoting different elevations, these equipotential lines also denote different potentials. Or you can think of it as elevation too, because that's a change in potential energy. If we have a more complicated configuration like this, and y'all did this in lab, my equipotential lines, they would start going perpendicular to the field lines at each position. Right here, it's perpendicular all the way around. Something like that. If I'm looking in the middle here, what would the equipotential line look like at this point? Where would the equipotential line extend? To the side, up, curved around, left, right, what would it be? It would be straight up and down because it would go perpendicular to these field lines. Now notice, just to reiterate this, let's say that I have a charge right here, positive, negative charge, it doesn't really matter, and I want to move it along this equipotential line. How much work do I have to do? Positive work, negative work, or zero work to move this charge along this equipotential line? Zero work. I don't have to do anything to move it around. I mean, I don't have to exert any work, like moving around the mountain at the same elevation. All right, let's do this quick test. There we go. Oh. Okay. At what points is the potential at its greatest value? A, B, C, D, or C and D? You can sort of think of this as a topographical map, where this would represent the peak of a mountain or the bottom of a lake. What would it represent? The peak of a mountain, right. And as you go down, you decrease in elevation. Most of you have the right answer, but that helps you a little bit. I'm going to stop at 1 minute. 1 minute. Okay, awesome. So C and D have the highest potential. Again, you can sort of think of this as a mountain. Or you'll get a joke here in just a second, okay? But you sort of think of this as a mountain, looking down on the top of a mountain, and my plus Q is right here. And then I have an equal potential line right here at point C and point D. And then I have an equal potential line right here, and an equal potential line right here. This is point A, this is point B. And as I move outwards away from this charge, my potential decreases. Similarly, as I move outwards away from the plus Q at the peak of the mountain, my potential decreases. Now, be careful because we can also have negative potential, and so if this was a negative charge, I would have to flip it the other direction. All right? Are you clear what I mean by that? Because V is KQ over R, if you want to think about this mathematically. V is KQ over R. If R is small, that means that V is big. If R is small and Q is positive. If R is small and Q is negative, then I just get a big number, but a negative number over here. Potential can be positive or negative. It's not a vector quantity, but it can be positive or negative. It has to do with sort of the relative energies of those things, the charges. Yeah? Let's ask some questions. Oh, how do astronomers organize a party? They plan it. That was too easy, wasn't it? All right. Are we probably going to come back to this, okay? Though it won't be on the exam. No capacitors on the exam. But let's do some clicker questions right now. We've done some of these, I think, correct? That's correct, we've done some of these? Okay, give me just a second. I need to, I figured out a way to fix this thing. Just give me a second. I'll be right back. I'm not going anywhere, but... Alt-tab. That's what they tell me to do. All right. Alt. That's all right. I'm sorry. I have to figure out what question we end on last time, y'all. 2.2. We're at 2.2. Were you trying to trick me to go past it and show the next one? This one?
Yeah.
All right. I will fix this clicker. I have to figure out what's going on. All right. So then we have two charges come together. Which two groups of these charges, the first, the second, require more work to bring them together from a very large initial distance apart? Remember, we can think of this work to bring these charges together is the same as their potential energy. Not their potential, but their electric potential energy. We call that U. So which of these require more work or contain the most potential energy in this configuration? Is it the first one, A, B, or are they both the same amount of work? We're doing really well. All right, I'm going to stop at 108. 108. Okay, that's awesome. Wow. It's actually quite good. So think about this in a couple of different ways, and this is the way I suggest you think about it. U is KQQ over R. Right? That's the potential energy of two charges. If I have more than two charges, I look at each individual pair in that configuration. We worked a problem like that last time. So if I think about these two charges, the potential energy is K, 2Q, Q over D. Right, that's the energy that's associated with that. Now looking at the second one, U is this energy plus this energy plus this energy. So I would say K QQ over R plus K QQ over R plus K QQ over R, or D. I'm using D instead. And so notice this has 3 times this value, whereas this one only has 2 times K QQ over R. So this one contains more energy just because of the configuration. Even though you still have the same amount of charge, like you still have a total of 3 Q charges, because of the way that they're arranged, they contain more potential energy. Okay? You did well on that one. That was good. I expect you to not do very well. Wait, that wasn't very affirming. Okay, what is the electric potential at point A? At point A, I have this point, I have a plus 50, a minus 50. At point A, over here, I want to know what is the potential. Is it 0, equal to 0, or less than 0? I'm going to stop at 40 seconds. 40 seconds. Okay, awesome. A is right. It's greater than 0. The reason is I'm closer to this positive charge. This positive charge exerts more of a potential at this point than does the negative charge. The negative charge exerts a negative potential at this point, or it creates a negative potential at this point, but it's further away, so it creates a lesser negative potential. So I have more positive than I have negative, so the net potential is greater than 0. Oh, this might be inappropriate. It's a little vulgar, but I know that we're amongst friends here, right? I'm not even sure I should tell this here. No, we'll just sort of hold it for the next one. Okay, listen. But don't get me in trouble, okay? So, I sort of had this idea that I would call my bathroom Jim. Because what do we usually call the bathroom? John, right. I just thought in the morning it'd be so much cooler to say, I'm going to go to the gym now, instead of saying, I'm going to go to the Don now. What? It's a little vulgar. Any potty humor is just, it's like middle school. Okay, what is the electric potential at point B? So they probably told me that joke. All right. What is the electric potential at point B? All right, we'll stop at 20, 25, 25. Just ask your neighbor if you're not certain. Okay, good. B is right. Listen, at point B, I have a certain potential due to this positive charge, and then I also have a certain potential due to this negative charge. That potential is V equals KQ over R. Remember, with potential, you keep the signs. Let me just sort of summarize that, by the way, over here. You know, as I said, we have a bunch of different formulae. I have this F equals KQQ over R squared. I have E is KQ over R squared. I have V is KQ over R. And then we have U, which is energy, is KQQ over R. So we got these formula, and they all look about the same, and we're going to see them on this next test. We're going to see all four of them, doing calculations and doing various thought experiments with them. Just sort of want to keep these straight. You might want to put them on a 3x5 card and just paste it to your mirror, your cupboard, or wherever you keep things that you want to look at. But I also just want to remind you that we don't use signs for these two. Like if the charge is negative, we don't put a negative there. Instead, we do this thought experiment where we say, what if I put the charge here, what is the direction of the force that it feels? Okay, so we figure out the direction of the vectors before we start doing calculations. But over here, with these two, I do include the signs. These are both scalar quantities, but they can have a negative value. It has to do with the relative energy of the charge configurations. So practically what that means, if you have a negative sign, you put a negative sign in these calculations, but not in these. These are vectors. They're a little more complicated. But with the scalars, you have to include the negatives. So hopefully that'll help you to sort of keep all these K's and Q's and R's straight in your head. But as a practical matter, you want to use negatives when you have a negative charge. So in this case, the voltage of A is KQ over R. The voltage for B is also KQ over R. The R's are equal, but notice that this charge is negative. So the total voltage is equal to 0. They cancel out. When I'm equidistant between two identical charges, the potential due to those two charges is 0 because they cancel out. Okay? What is the potential here? Just blur it right out. Without any reserve. Is 0, right. So because I'm equidistant between those two charges. All right, 4-point charges are arranged at a square. Describe the electric field and the potential at that point in the middle. Put in your answer if you haven't yet. All right, I'm going to stop at 40, okay? 40. Let's take a look. I assume that's D. I'm going to trust 83% of you. Now let's take a look and see what the answer is. I don't know right off. So let's first look at the electric field. Due to this charge, the electric field is there. Remember, I imagine a positive charge in that point and ask myself, what is the direction of the force that positive charge feels? And that's the direction of the electric field. The electric field due to this charge is in this direction. The electric field due to this charge is in this direction, and the electric field due to this charge is also in that direction. Yeah, so the electric field is bigger than 0. The net electric field is in this direction. You're going to have some questions like that where you have to ask yourself what are the different vectors that are at work here, either be force or electric field, on the exam Monday. Then you ask yourself, what about the potential? Well, I have 2 positives and 2 negatives. Because they're equidistant from the point in the middle, they both cancel out. So I get KQ over R, KQ over R, K negative Q over R, K negative Q over R. Those all add up equal to 0. At what point here, hey, it came back. At what point does D equal 0 here? All right, I'm going to stop at 40 seconds. 5 more seconds. Okay, good. All of these. They're all zero potential because they're all equidistant from those charges. Okay? You read the paper? There's a kid napping at school? It's okay, he woke up. You were scared, aren't you? He's like, oh, that's probably my kid. All right. Which of these configurations gives V equals 0 at all points on the x-axis? Or which of these, or all or none of these, give you a potential equal to 0 along all points on this axis? Right. Let me show you. I'm going to show you one in case you're a little confused. Because the answer is not D. But let's take this one. If I take a point on this axis, look, I have a longer distance from that charge than I do to that charge. So the potential of those two charges, they don't cancel out at that point. So here my potential is not equal to 0 because I'm at different distances to those charges. Now there is a point, a single point on this line where the potential is 0. Where is it? In the very middle of the square, the potential is 0. But all along the x-axis, not equal to 0. It's either positive or negative. What about the other two? I'm going to stop at 125. So you got about 8 seconds and decide your answer. Okay, awesome. A is right. The reason is, let's just pick a point. On all of these, the very middle point, the potential is 0. Like, for example, this one right here, I'm equidistant from there to there, there to there, so the potential is 0. But let's look at this one. Let's go a little bit off from the center. The distance from there to there is the same as the distance from there to there, so the potential is 0. Similarly, those distances are the same, so the potential due to those two charges is equal to 0. So I can have a 0 potential all along this line. That means that it doesn't take any work to move a charge all along that line. I can move a charge there without any work at all. It's sort of like a well, right? Or a deep freeze that you lock your little brother into, and he's like this tall. All right. Which of these on the y-axis? Similar question, just on the y-axis. I think they're even the same configurations. On the y-axis, meaning an axis that runs like that, are all points at v equals 0 along the y-axis. All right, I'm going to stop at 40 seconds. 40 seconds. Okay, awesome. C is right. For the same reason, look, I'm equidistant between these charges, but on these others, I'm not. I'm either closer or further away from the positive or negative charge, so their potentials don't cancel out. All right? Tell me what y'all think. Do you think that a kangaroo can jump higher than an Empire State Building? Of course he can. Empire State Building can't jump. All right. Which 2 points have the same potential? Can y'all see that? Sorry, it's actually a very similar question. Does it show up in your workbook okay? The bigger, okay. All right, there are circles here. Just look at, if you don't have your workbook, we'll sign with a neighbor, please. All right, I'm going to stop at 35. 35. Awesome. B is right. They're at equal potential. It's like those topographical lines on a map, right? Like walking around a mountain at the same altitude. It's the same potential energy, so you also have the same potential. In this case, we're talking about electrical potential. But they're on the equal potential line, so they have the same potential. That's E and C, option D. All right, which of these require the most work? I want to move a positive charge from point P to either 1, 2, 3, or 4. Which of them requires the most work to do so? I'm going to go away for just a second. I will come back. All right, let's stop at 50 seconds. 50. Oh man, that's awesome. I was not expecting that. So if you imagine this, if I have a positive charge here, it feels a force from the electric field in this direction. So if I just let this thing go, it's going to fly off in this direction. The hard part is going to be pushing it from here back in this direction because I'm pushing against the force of the electric field. So that's what's going to require more work. Which one requires zero work, or do any of them? Which requires zero work? To go to place 1, 2, 3, or 4? Or they all require the same amount of work? Zero or not zero? All right, let's stop at 25. 25. Doing pretty well. C is right. Listen, guys, equal potential lines run perpendicular to the field line. So this path is along an equal potential line. Requires zero work. Hey, fellas, Cody, y'all sort of, I'm not sure what y'all are doing, but don't disturb other people, please, okay? All right, let's look at capacitors. All right, listen. Y'all glad we know what forces, fields, and potential? And now we're moving into a whole other sort of different part of the course where we're going to use a lot of those ideas, or at least we're going to use the idea of potential, but we're going to use it in more practical ways, dealing with circuits. So we'll look in this chapter, actually, we're going to look at capacitors and circuits, and then in the next chapter, we're going to look at things like Ohm's law, which I did for a lab, or you will do it for lab soon. And we'll look at resistors in circuits, and we'll look at capacitors and resistors, so-called RC circuits. So we're going to spend a lot of time on circuits. In fact, the next exam might be all circuits. Ooh, that's fun, right? Some people like circuits, but I have to tell you that some people don't like circuits. You know, in the past I've said that this test you're going to take on Monday, that is the hardest test. But I think that it's because forces, fields, and potential are kind of abstract concepts, and it's kind of hard to wrap your mind around. Circuits, on the other hand, they're really simple rules, but you have to apply them to complex situations. And so some people are really good at that, and some people, you know, it takes more work, but they can still do well at that. I think circuits are easier than potential, but that's just me. So let's look at capacitance. And we're going to be dealing with a parallel plate capacitor. We can see some other types of capacitors, but that'll be the one we'll look at. And a capacitor consists of two metal plates of area A separated by a distance d. That's all they are, just two metal plates. In fact, we'll watch a video a little bit later where that was the first capacitor they built. They took two metal plates and they put them like this. They actually put a piece of glass in between it to keep them from touching, but it was just two metal plates. They were about, you know, this big or so, and they put them so that they didn't touch. They had a certain area, they were separated by a certain distance. And when you connect it to a battery, the capacitor becomes charged. And this was really the big deal about capacitors, that the capacitors can become charged and it stores energy that can be used later. In fact, we'll see that this purpose is really the main purpose of capacitors. We'll see another slightly different purpose, but it really is just a variation, that I take a little bit of energy and I save it for later in an electrical circuit. And then when I'm ready to use it, I can use that energy. All right? So if I connect it to a battery, I get positive charges over here, and I get negative charges over here. Now, each plate will have the same charge. We can think of this as either charging by conduction or charging by induction. Which is, like, if I put some positive charges over here, and I get negative charges over here, the equal amount of negative charges, is that charging by conduction or charging by induction? Induction, right, because that doesn't require contact. Charging by conduction requires contact between two surfaces. But if I put positive charges on one plate, and I get negative charges on the other plate, that's charging by induction. You can think of it in that way. The capacitance of a capacitor is defined by the amount of charge it holds with a certain potential difference applied. Or a certain voltage, if you want to call it a voltage, and I'll usually call it voltage from here on out. So if I think of, I have plus Q on this one and minus Q there, I have this plus and minus Q charge, and you might think, well gosh, it has 2Q, right? But we're just going to call the charge on the capacitors Q. All right? So the capacitance then is defined by the charge that it holds, Q, with a certain potential difference over V. So C is defined as Q over V. If I apply a certain amount of potential, how much charge do I get? You measure these two, and these are not that hard to measure, it turns out, and I define what is my capacitance. So that's one way to define what is the capacitance. Those of you that have had the Ohm's Law lab, by the way, this is sort of like Ohm's Law for capacitors. I know not all of you have had that, but you're about to have it. This is sort of like Ohm's Law, but for capacitors. And unfortunately, there aren't any good experiments to do on capacitors in that lab, so what's it going to do? The units of capacitance are the farad. This is after Michael Faraday. I'm going to call him Mike. Because, you know, he and I, like this. He died a couple hundred years ago, I guess. But it's the farad, and because it's a name, you capitalize it. 1 farad is equivalent to 1 coulomb per volt. Capacitors don't usually come in farads. They are usually much smaller. A farad capacitor is a really, really big capacitor. Just like a coulomb is a really, really big charge. So just to remind you, you know, we're going to use micro and nano a lot still, 10 to the minus 6, 10 to the minus 9. So just, you know, get those wrapped around in your mind because you'll see them a lot. So in the above figure, if, you know, we had the 12-volt battery, if the charge was 24 microcoulombs, then C is Q over V. Then the capacitance would be 24 microcoulombs over 12 volts, which is 2 microfarads. Often, and I think maybe on your equation sheet, or often we'll write this relationship not as C is equal to Q over V, but instead as Q equals CV. In fact, that'll probably be the way that I write it from here on out, as Q equals C times V. And like I said, it sort of looks like Ohm's law a little bit. I think of it a lot in terms of Ohm's law as well. All right, let's try this little quick test. All right, I'm going to stop at 42 or 43. Let's go to 43. Okay, good. Let's see. A is the right answer. The one that has the most charge is the one that has the most potential. Q is equal to CV. You can think of it, I'm putting more energy on this capacitor. Because I'm putting more energy into it, I'm going to get more charge. All right, more charge is equivalent to more energy. So if I apply more potential, I get a bigger charge. I have more potential across C1. Now for parallel plate capacitors, the capacitance is dependent upon the geometric proportions. Remember, we have 2 things that define our capacitors. 2 measurements. Do y'all recall what they were? Area and the distance, right. Plates of a certain area separated by a certain distance. So I have A and D. Now let's just sort of think about this. I want to see how you guys answer this. I think that you'll probably answer it correctly. How is the amount of stored charge affected if you make the plates bigger? So you keep the same voltage, you keep the same separation, but you just make the plates bigger. How does that affect the charge that they hold? Do you think that the charge it can store more charge, store less charge, or will it store the same amount of charge if you make the plates bigger? So we'll stop at 35. Okay, good. A is right. You might not have any a priori reason to think that, but you know, you get a bigger plate at dinner, you put more food on it, right? If the plate gets bigger, there's just more places for charges to be stored on it. So it's sort of intuitive in that way. So what we have here then is that the capacitance is proportional to the area. If I have a bigger area, I have more capacitance to store charge. I can think of capacitance as the capacity to store charge. Let's look at the next one. How does it vary with the distance? So how is C proportional to D? If I increase the separation between the plates, how does that affect the amount of charge? This might be a little bit more difficult to imagine. If I pull the plates further apart, how does that affect how much charge they can store? We'll stop at 35. Okay, good. Many of you got it. That's okay if you didn't, because, no reason for you to have gotten it. But basically, if I pull those plates further apart, you can think of sort of I'm diluting the energy a bit. I'm spreading the energy over a bigger area or a bigger volume, if you want to think about it that way. But the result is that the capacitance is inversely proportional, not to the area, but the distance. So I have these two expressions. C is proportional to A, C is inversely proportional to D. So now I can write another expression for C, which is that it's equal to A divided by D. And then we also have this proportionality constant. Don't worry about that. It's called the permeativity of free space. Well, you do need to worry about it. It's on your equation sheet, the value for it, but you don't need to memorize it. It has a value, I think it's like 8.85 times 10 to the minus 11. And that's in farads per meter. Isn't that right? It's on your equation sheet, all right, the value. Huh? Scroll down. Oh, yes, there it is. Okay, awesome. It is in this units, but it's also, you can think of it in terms of farads per meter. All right? You'll have some questions on exam 2, not on this coming exam. We have to just calculate the capacitance. I give you some dimensions, and you have to calculate the capacitance. All right, let's try this question. So here you put some charge on a capacitor, and then you take away the battery. So that capacitor has that amount of charge on it. Then you double the area of the plates. What's going to happen to the voltage? I'm going to help you out just a little bit. Let me show you, guide you a little bit. So I know that C is equal to epsilon naught A over D. And I also know that Q is equal to CV. Notice that if I double the plates, that doubles C. Q remains constant. So I want to know what happens to the voltage if I double the area of the plates. All right, let's stop at 115, 115. Okay, so look, if C increases by a factor of 2 and Q remains constant, that means V has to decrease by a factor of a half. So it was 12, so yeah, C is right. All right, let's see what else we got here. Dielectrics. So a dielectric. Dielectric is just a material that you put between those two plates. I want to show you a video. I think now might be a good time to show it to you. Okay, give me just